the next Union Stage speakers in the agenda is the following one. So we will have Roman, who will talk about concurrency matters, test it or regret it. Then we will have Twancott, who will talk about autoscaling, and it's going to be another song of our friends Led Zeppelin with a Stairway to Heaven or Hell. We will then have Stefano Doni from Akamas, who will talk about Java performance in 2021. And last, we will have Taras Tugiri, who will talk about old pattern powering modern technology. So let's start with our first first performance rock star, in fact, and I'm referring to Roman. Roman is coming from Vienna. He is founder of Triscon. It's an Austrian consulting company doing a lot of performance testing, performance monitoring, performance engineering, a lot of delivery around that space. So he will share his experience more on that part. So here the topic of today is concurrency matters, test it or regret it.
Thanks for the kind introduction. I'm going to focus on one specific subject. It's about concurrency. I think it's purely underrated. So the last time, as you mentioned, I was talking more about Captain, automating performance tests. Today it's a complete tech talk about concurrency problems. So just before we get started, what are you going to see? So first of all, I thought if you've never heard about concurrency problems so far, it might be interesting to have some real-life examples. I brought some of my own career, and I also looked up a little bit in history. Then we're going to do a little bit of theory to finally understand what is a concurrency issue and what is not, and why it is important to test it. And today, it's all about how to test it. I'm not going to focus on how you can avoid concurrency issues in programming with locking threads, synchronizing and stuff like that. I'm not going to focus on that. I'm going to focus on the root cause of problems and the implications and how you can actually test it. Because if you look up concurrency problems in the internet, you will find a lot of stuff, but you will probably not find explicit concurrency testing. And I have prepared a demo, of course, using NeoLoad with an application that we designed consisting or having a concurrency bug that I'm going to reveal during the demo. So let's get started. You already mentioned Triscon. I'm the founder. We're in Vienna. If you're ever in Vienna, just flick us an email or give us a call. We can have a chat about performance. We deal with all aspects of performance engineering, also APM, Dynatrace partners, and we offer several workshops and trainings. And let's get started. Why is it important? I mean, concurrency, you have heard about it before probably. And but what in history what were the interesting cases? And I came up with little information there, unfortunately, but there are some concurrency problems that are stated as concurrency problems. One is Therac 25. So there was a radiation therapy machine back in the 80s, which in some cases pulled out way too high radiation doses, which had, of course, huge implications for the patients because they received 100 times more radiation than they should. Another case was a big blackout in 2003, which is also related to this so-called concurrency subject, and the entire electricity network collapsed during this in this northeast region. It could have been just a local event, but due to a concurrency bug, the alarm system didn't go off properly, so they were not able to deal with it. Now you can say, well, this is like 20 years ago, but there is recent cases. I brought some of my career, and today I actually want to invite you to share your stories as well. Of course, we don't need to name customers or applications, but what I faced in my career already is there have been prices wrongly computed, meaning that person A is computing something that is cheap in some software. In the meantime, almost simultaneously, person B is computing something very expensive. And suddenly person A is receiving a huge price, which he didn't expect. and he shouldn't. And if you ever face this kind of problem or similar problems, it's most likely a concurrency problem. Another thing is if person A and person B are retrieving documents, so those might be shipped wrongly. Also a case from a production incident that I was investigating some time ago. And of course, there it gets really interesting because this is GDPR relevant. So it's something that companies have to take as important. And these are the really hard to track failures, I'd say, if something gets mixed up. But sometimes it's more obvious. Sometimes it just crashes if two people hit the same button. And this is also often related to concurrency problems such as deadlocks. And today, I want to focus on all these kinds of problems and where they originate from. So what is it? So let's start with the basics. Today it's a little bit educational. So where does the word even come from, concurrency? I looked it up. Its origin is probably Latin, and it means to run together, assemble, hurriedly, clash, fight, or to happen at the same time. And this is where it's already getting a little bit tricky, because to happen at the same time could also mean to run parallel. But it's not about parallelism, and I'm going to distinguish between concurrency and parallelism. So if you ask Wikipedia, they tell you it's about overlapping time periods instead of sequentially. So in a computing farm, if you ask Rob Pike, he's going to say concurrency is about dealing with a lot of things at once, and parallelism is about doing a lot of things at once. So I guess I have confused you now to an extent where we can proceed onwards, and let's get some clarification, like what is concurrency really? And I found on the internet, maybe you know it, some nice thought experiment. It's called the dining philosopher's problem. So we're not inside computers now, we're on complete abstract level. And the idea is that you have 5 philosophers sitting at the table, and they want to do 2 things. They think and they eat, and they either think or they eat. So, but to be able to eat, they need 2 forks to eat their spaghetti, as you can see in the image. And there is only 5 forks for the 5 philosophies. So it is simply not possible for them to eat at the same time. But you don't want any of these persons to starve, of course. So you want to make sure that everyone gets a bite and then the next one. And there can be, in this setup, situations where, imagine, everyone grabs the left fork and they are waiting for the right fork to be available. It will never happen because all the forks are in the left hand of one person and they won't put it back. And this is what we call a deadlock situation. It won't change anymore and you've already lost. So by having this simple problem of having philosophers sitting on a table, you can actually link back to concurrency. This is concurrency. You have a shared resource. In this case, it's just forks. You have philosophers wanting to eat their spaghetti with 2 forks, using these limited resources. And we're going to translate these person and forks into actual requests and threads on the next slide. But let's stick with this a little bit. So what is concurrency and what is parallelism in a more simple way explained? Concurrent, if you have a coffee maker, you could think of it as 2 queues, and one queue gets a coffee, then another queue gets a coffee, but you won't be able to serve 2 coffees at the very same time. If you have a parallel system, it means that you have 2 queues and you're able to pull 2 coffees at the same time, and you see already where this is getting. So this is basically the CPU cores. So on one core, of course, you can have concurrency, but on one CPU core, you cannot have parallelism. You need multiple cores for that. But let's have a look at it. So we have a core. And just as the philosophers wants to use the fork, we have multiple people requesting sites on our web server. So eventually the site needs to be shipped out from the server, and this has to be processed on the CPU. But what's happening inside there? What's really going on? So these requests get translated to individual threads. I'm going to explain it in a brief way on the next slide. Let's just stick with it. So we have requests coming in. You want your site to be shipped, and those get translated into threads, which are then executed on a core on a CPU. And you can, of course, execute different threads on different cores, but there will always be only one thread at a specific amount of time executed in one core. But those will be heavily rotated. So it will not be as with the coffee maker. So it just doesn't work the way that you have one thread, one coffee being pulled out entirely, and then the next one comes. So it's like Mambo number 5. You get a little bit of this thread, then you get a little bit of another thread, and hopefully everyone gets a piece of the spaghetti. So this is how I explain concurrency and threads. So what are threads exactly? I've mentioned them. It's just a small sequence of programming instructions, like breaking it down even on more little pieces so that they can be executed on the operating system in your CPU. So you have your program somewhere, and it's loaded into memory, and you have your shared resource among the processes, which generally then contain your threads. So your shared resource is, in this case, your memory, your RAM. And all those threads, or some of those, may share the same memory. And this is where it gets interesting and where concurrency problems can occur. So how is this actually working? As I said, it's heavily rotating the execution. So usually a scheduler is taking care, it's part of the operating system, to decide when which thread is executed. If you think about back at the dining philosopher's problem, so you need some rules, right? You don't want them to starve. You need to decide either if when one person can eat, or when, in this case, one request or one thread can be executed, and when the next one is on its order. So you need a set of rules, and this is a highly complex matter, and many things can go wrong. If you look in your task manager, this is working on each machine. You will end up with a number of probably 4 digits, 3,500 threads. It was yesterday on my computer, and you see also your clock speed, meaning that about 2.4 billion times there can be a few bits shifted in your CPU within 1 second. And this is the reason why multi-threading is actually possible, because you can shift between all those threads within 1 second, and you can do multitasking with one CPU. You don't need parallelism for this, just to distinguish. So now that we have some, let's say, rough idea what concurrency is and what threads are, let's deep dive into the problems. So in a happy case, we have a thread, and what it's doing is it's following some program instructions, reading a value, increasing the value, writing it back. So you end up first with 0. After it's done, the value is 1. Again, the value in this case is a shared resource among another thread or among more threads. So the second thread reads the value, it's 1 already, increases it, and writes it back to the final value 2. In a disaster case, as I call it, it can happen, as we have learned, that not each thread is executed entirely, and then the next one is executed. It's like not with the coffees in the coffee machine. So it can happen that the first thread reads the value, then the second thread gets a little bit of CPU times reading the value. Well, both 0 at this time. Each of them thinks they increase the value to 1 and writes them back. So you end up with a different result. And this is really, really bad, because imagine if this happens if you have shared resources, something like personal IDs, authentication tickets, or even a bank account balance. You don't want these things to, or document IDs, you don't want these things to get mixed up. And if you think nowadays, well, these things don't happen anymore, I can tell you they do, and they do a lot in many different sites. And I'm really excited to hear your stories. So how can we actually test it? What can we do to prevent this? So performance testing is obviously the right tool for this. But what we do in performance testing, well, this is some performance testing educations now. For me, it's a superset. It's a terminology where it can mean a lot of things. We also call it load testing, would be often used term if you have a load on a system that is expected volume in production or something like that. But it's really always driven by the goals that you set for your test, what test type you need. So there is stress testing, and you focus there on what happens if you put heavy stress on your system or increase the load, how is it behaving? Do the response times get back to normal afterwards? So we focus on this. We do endurance testing. We want to see, are there memory leaks in your system if we have a constant load over a huge long time frame? We do failover tests, like to pull out one plug of a system, even do chaos engineering, see if everything works. We do spike tests to see in these events how do the response times behave. And to achieve all this, we have one instrument. We have our load pattern. By playing with the user load, we can actually achieve all these tests, right? So we have many different scenarios here. We have sizing tests to determine, for instance, in cloud systems, how many cores you need for your microservices or whatever. And we also do scalability tests to see how the system is scaling. But actually, there is no test out there that tells you to specifically focus on concurrency. And what is it? It kind of is assumed that if you run the proper load test, this is like implicit. I don't need to do concurrency testing. And I say, maybe, but maybe not. And you can actually, with very, very little effort, achieve something like a concurrency test. So what you actually want to do is, instead of what you usually do with your user load, like having a smooth ramp up and then putting your production load on the system for an hour or so, in this case, you want it to be in the complete opposite way. You want your virtual users or your requests to be heavily synchronized. You want to have as much, in this case, I call it concurrency or concurrent users as possible at a given time. So if you imagine a system where you have 3,000 users active each day, it's not so likely that you have like 2 or 3 users hitting the same button or even 20 at this very same second. So if you design a test where you have only a few users which are highly synchronized, you can achieve already a really high concurrency rate and see what's going on there. And what is it actually that you should focus on? You should focus on, of course, if there is errors, to see if there are deadlocks occurring, or if there is data mixed up. And you can do this. You can actually validate what you're getting back. You do this anyway in your load test, right? So if you have some form, you know the outcome, you can validate if the response still matches to your user session. And if there is errors, of course, you will immediately see this. How can you achieve this highly synchronized test now? And how can you make your users not like one run faster or slower than the other? It's with NeoLoad quite easy, actually. You can just do pacing and rendezvous points, and I'm going to talk about that a little bit more in a second. So I'm going to show a demo of a registration process. This is already a screenshot from this. Pacing in NeoLoad is different than think times. And of course, most of you performance engineers are probably aware of this, but I think it's so important and such a powerful tool that I want to explain it a little bit further. So pacing is the minimum time for a transaction or a user path. If you have a think time of 1 second between one transaction and the other, it means that one transaction is executed, then 1 second is a delay, and then the next transaction is executed. By having this test design, you will make yourself very dependent on how fast your web server is giving you an answer. I call this, and you will not find this in any books, I call this reactive test design. And with pacing, you can achieve something like non-reactive test design. So you do not depend on the reactions, how fast your web server is answering, because if you use pacing, it works like this. If you say, I pace this transaction to 1 second, to 3 seconds, and if it then takes 1 second, NeoLoad will wait for 2 more seconds. If it takes 2 seconds, NeoLoad will wait for 1 more second, so it will always proceed after 3 seconds, meaning that if your web server becomes slower, you do not generate less load, and if it becomes faster, you do not generate more load, which would be, in my case, as I call it, reactive test design. So this is not only important for concurrency testing, but as you can already see where I'm getting at, it helps you to synchronize your users if you want this as well. And you can actually, and this is a really neat feature for concurrency troubleshooting in NeoLoad, insert rendezvous points to synchronize your virtual users. This is something that I'm going to show you like on a hands-on experience. And of course, as I mentioned, it's important to validate. It's important to validate your load tests, your responses. And of course, it's not often feasible to validate each individual form field if the data is still consistent in there. But this is where it comes into place, that you have to think about where you can imagine that concurrency problems may occur, and talk to the developers. And if you're already aware of some implementation that may be problematic in this matter, make sure to put in some extra effort for your validations in there. So now we've already reached the demo time. So I prepared a little demo for today. And first of all, I'm going to show you first of all, because it didn't work the last time, give me a little bit of feedback. If you can see my screen, you should see a web page with some usernames and registration date before I proceed onwards. I hope you can still hear me. Maybe Henrik, a little bit of a sound effect or something, if we're good to go, is fine. Just want to make sure that you can actually see my screen.
We can see your screen and we can see.
Perfect. So what you see is actually the Triscon testing turf. It's an application that we wrote once for our recruiting challenge. If you want to work for us, make sure to check our website. You will face a similar challenge to what I show you now. And another thing is for educational purposes such as this. So we developed this thing here, and it's a registration process. And I can enter something here, register for the pack heroes, and I have to enter some email address. It has to be different each time, and of course I need a password. And if I hit register, then I will end up with a new user in the list, of course just the user, and when it's registered. So this is quite easy to script, and as you can see, it works just fine. So let's move to NeoLoad. So we have NeoLoad here, and this very same process, we call our Triscon testing turf. We navigate to this register form, and we submit the register form. So in there, I could already put in the validation if my username is actually appearing in the list after I've registered, if I know that this should be the outcome, right? So this is what we do. And now I want to show you one thing. So we have a couple of different scenarios here, and one would be a traditional, I call it traditional ramp up. So nothing special. I do have some pacing. I'm gonna run here the ramp up test for this one, register v2 up to 20 users. It's this test case that I just showed you. We have some 2 seconds pacing in there. And I'm going to put in one user each 19 seconds here. Just some random setup. And I'm going to execute this. And soon we should actually see now that the users are coming in here. So as soon as NeoLoad is spawning now the first user, we can actually spy on him here. I really love this view. Thanks, Neotys, for this. Sometimes I enjoy watching what the virtual users are doing during the test. And so here we're actually already doing a load test. As you can see, some users are coming in, those are created, and everything seems to be fine so far. Let's move back here. So we have another user putting more load on the system. each of them is working with the very same test case. So we have one population, one user path, only 3 transactions. To keep it simple, I have here the pacing of 2 seconds on each transaction, meaning that this total test case should take 6 seconds. What I love to do then, I want to share a little bit of my best practices here, is I put another pacing duration on the actions container with a little bit of a buffer, because sometimes you may not end up with the same number of transactions you may not be finished within the 2 seconds. So if it takes longer than 2 seconds, the entire process will be above 6 seconds. So you give it a little bit of a buffer here. What does this help you? It actually helps you to not execute more test cases within 1 hour. And the way I define load, it's always business driven. So you want to think about in test cases or workflows per hour that you want to do. And if you want to make sure that you do not do more or less in this case, this is the instruments that you need to actually achieve this, what I call non-reactive test design. So as you can see, we're already at 7 virtual users. Everything is still fine. Let's have a look back. If I refresh here, the site is still up, right? So we see more and more users coming in. And what I'm actually going to show you in a minute is what happens if I do this with a specific intent of concurrency testing. So not this traditional step load, but if I want to have my users highly synchronized. And first of all, we're going to wait for this test to be finished. It's set up to run only 3 minutes. And there you go. With 9 virtual users, we have revealed some error. Let's dive into this. What is it? So here you see in NeoLoad that there is something wrong with the dictionary. Apparently there is the same item already in there, and the register process suddenly failed. Okay, so this is something as a performance engineer that you would probably address, write a defect or even fix it yourself. And so it's something to consider. But how can you actually be sure that you trigger these things in your load test? And of course, if you have huge load, like thousands of users, it's very likely to reveal those. But my message is not like to do not this test. My message is that you can reveal those errors with less effort. And I'm going to show you how. So now I have the pacing set up here. And as soon as I have pacing, I have highly synchronized users, right? So only with 2 concurrent users, if I want to start them at the same time, I should be able to reveal this error, which is awesome. What I want to say you is if you have your scripts already recorded and you have your pacing defined, it doesn't hurt to run this in a calibration run to see what happens if you have like a concurrency rate of 5 or 10, and probably no one will even be mad, and because you're not putting huge load on the system if you do not do this in a proper load test window. So you have a lot of more flexibility instead of hoping to reveal those errors in huge, tremendous load tests with insane user load. So as you can see here, 2 users is enough if they are highly synchronized. In this case, of course, it's a demo. We trigger this if it's in the same second. But as you can see here in the previous test, on the test design, I'm going to stop this test. It was at a rate of 9 virtual users. So it's almost a factor 5 in difference of load that I had to put on the system to reveal the same error, right? And what happens if you have the case, someone is calling you saying, oh man, we have some weird stuff going on. There is documents mixed, people are facing weird errors, and you already suspect that there is a concurrency error. This is the time where you want to make use of rendezvous points. So I have a similar test case, or the same. I inserted here a rendezvous point. You just drag it in there. You don't have to do anything else. And then you define a rendezvous policy in NeoLoad. I've done this. I've did this here for the scenario. So this happens only in here. You say in the rendezvous policy, where your users should meet. I say, well, meet at this point and release those 3 users when they release it when 3 users are at this point. So you can make them be synchronous again. You can synchronize your users with this. Why is this important? Why do you need this if you have pacing? If you have like super exhaustively long test cases, it's so easy to just put in a rendezvous point at the end and you have your users synchronized again to test concurrency at the specific transaction late in your test case. So let's see what happens there. And it's pretty cool. As I said, this view in NeoLoad where you see what the runtime users are doing, I like it a lot. You can even follow individual virtual users. So this is the same scenario that I showed you before. It's the step load pattern, yeah, right? We are starting with one user. After 19 seconds, we will add another user. And the first user is already waiting at the rendezvous point. And the second user is now spawned, is calling the site, is navigating to register, and he's not submitting. He's waiting for the others. And this is actually the best way to achieve forced concurrency, because you can be sure that the next step is going to be executed at once from all your virtual users. So now we have the third user. What should happen now? They should proceed onwards. As you can see, they hit the submit register button. And what should happen? We should reveal our concurrency error. And this is exactly what was going on here. So the things that I explained here, those are real things. They exist in applications. They exist in old applications. They exist in new applications. And only with performance engineering and proper tests, you can reveal those errors. And once they are in production, they are incredibly hard to track down among systems with huge architecture, a lot of services involved. You will probably take a lot of time to reveal this error. So to conclude for today, only 2 more slides to watch the time a little bit. I also want to talk a little bit about the characteristics of performance engineer. This is actually from one of our methodology trainings. It's what I tell people when they first get in touch with performance engineering. So what are the soft skills? What does a performance engineer have to deal with? You have to be very communicative. Of course, you need to understand the application you're testing. You need to get your non-functional requirements. You need to be diplomatic. Even especially when it comes to communicating failures. And you need to be patient. You should be, and this has been stressed today, a lot technically skilled. Of course, in the best case, you're like a hero who can deep dive into the mainframe as well as on OpenShift and AWS, right? You need to be stress resistant. I think everyone will agree to this. And I think it's a huge responsibility that you have because as you saw, those things can cause tremendous pain in production, and only with performance engineering you can reveal this thing. And one of the most crucial things is that if you communicate test results, you need to be understood by management. And you need also to be able to talk to technicians to get the technical information from applications that matter for your tests. You sometimes need to read between the lines because people don't tell you everything. It comes to how often a system is used, maybe. Of course, you have to like challenges. You need to know statistics, as we have seen many times today. And you need to apply scientific approaches, as, for instance, Dean does very well, as we saw 2 talks ago. And so if you combine all this, how could a single person have all these abilities? It's almost as if it's not humane, and it isn't. Of course, everyone has its strength, but since this is the pack heroes, I thought that if one person is really able to combine all these things, it would actually make him a superhero. Yeah? So, but this is not how it works. You need to work in teams, of course. Everyone has its strengths. But it's a nice way of thinking. I mean, what we are trying to do here is actually really, really important. And it's also a lot to ask from one person. And you will not get the fame of Superman probably, because if you do your job really awesomely well and everything is green and you're just like giving green light, go to production, there is high chances that you will not be thanked accordingly. But why do you do this? You do it because it's the right thing to do, and this actually makes you Batman. You don't do it for the fame. You just do it because it's the right thing to do, right? All right. So let's conclude for today. Concurrency problems can lead to really, really weird system behavior. And if you ever face it in production, it will be probably difficult to track it down, to even narrow it down where the origin is. So it's really, really helpful to catch these things as early as possible with components tests, for instance. And NeoLoad helps you to do this with rendezvous points, pacings, and validations. And now I actually would like to invite you guys to share your stories of concurrency problems that you faced in your past or in your career, or any things that you know about.
Roman, thank you a lot for this presentation, because I think it's really important to remind what is concurrency. And I think you make the point between people usually say, I'm doing load testing, so I'm doing concurrency. And I think it makes a lot of sense to remind the fact that rendezvous is there in most of the load testing products, and for a reason. And you just highlight that I think it's very important and meaningful for those who never played with the rendezvous.
Do you ever feel the need for more than the rendezvous settings in NeoLoad or any other tool? Because I find it sometimes interesting to have more options to play around with rendezvous.
Honestly, for my purpose, I was able to do actually all that I would. Maybe share your stories. What is it that you are missing for rendezvous?
Yeah, maybe my mind is not correctly with the tool, but I wanted to do rendezvous over multiple scenarios so that you hit the system at the same time. That was my issue, and it was not based on one script or one. It was like 5 scripts, and you need to add a rendezvous at the same time, which it was a bit tricky to set up.
I can imagine if it's multiple scenarios, probably works with multiple populations, but if you have multiple scenarios going on, then it's probably really hard to achieve this. I haven't faced this problem so far. Yeah.
But a great reminder that I need to do it way more. Sometimes I forget I can use rendezvous to use in the performance test.
Without mentioning any customers out there, because I have to say it is really hard to find something on concurrency issues. I think there is tremendous amount of issues out there originating out of concurrency problems, but no one is sharing their stories, and they have a reason, because these things are usually really causing tremendous pain, which you don't want to have public outreach with. But now with on a complete abstract level, no customer names, application names, what have you faced in your career so far? Any stories to tell?
I mean, I think it really depends on how the application has been designed. I think now with more and more Node.js, JavaScript, and similar languages, even Java has changed significantly over the years. There is more and more asynchronous programming, more and more. So building code in an asynchronous fashion is completely different logic, different challenges, different things. And I think those type of apps, definitely there is a lot of concurrency aspects to test, because you can be surprised.
Yeah.
Andreas, do you have any questions for Roman related to
yes, one question. After you find that you have some concurrency issue, what do you suggest to triage the problem? Like that you look in the code, where is the issue? Like if you have a complex system, do you have some advice or tooling how to actually find the issue after knowing there is an issue, like to find the root cause?
To be honest, I'm currently tracking down a concurrency issue as as fate has decided before I decided to talk about this here. And another colleague of mine called me today and says, like, it is insane now. We have a concurrency problem at a customer side there in production. So these are really hot topics still. So how do you deal with this? You have to distinguish if a concurrency problem is causing you to mix up your data, or that things get accessed which shouldn't, so contexts get shifted. These are really hard to track down. If you have concurrency-related problems where you have an error, you already kind of know or have a little bit of better grasp of where to test it. So from a methodology point of view, what I do is I look at the architecture of the system, and I try, for instance, to understand where's the data coming from, if some data is mixed in the service or something like that, and then I'm gonna put component-wise tests on these services, and I'm gonna go always more up and cover more with my tests in the architecture. If you're not in an initial shot able to reveal the concurrency error in an end-to-end test, I do it on a component-wise level, but it's a huge process to understand the entire flow, how the application works, how the components play together. And there is a feature from APM that I can highly recommend for this. It is request attributes, for instance, in Dynatrace. So it is in production highly interesting to know what are your method parameters, right? So you want to track down when something bad happens, and you can actually fiddle out call parameters or everything that happens in your code and pull and add this as meta information to your requests in production, and this helps you to narrow down concurrency areas because you then see when the problem occurs if you do this consistently for each service. And so these are the tools that I use. First, understand the entire system, run, of course, such concurrency tests, and get the most out of your APM tool as you can to have as much data as possible.
Comment and a question, actually. I really like the slide that you made on the superhero thing with Superman and Batman, and it's something that kind of comes up in conversations that, you can't build a company on superheroes, right? You have to have everyday heroes, the everyday people, and I liked how you framed that out, that you can't expect to just know everything about everything. So what advice would you give to a company that says, we've got a small team, we want to have superheroes, maybe we're not there yet, but how do we form this team and get there? How do we get to where we have heroes? How fast can you learn that? What are the skill sets we might need?
So I think the golden question is, how can you run an organization without heroes? How do you depend less on individuals? So this is actually the goal, I think. And one of the concepts that we are strongly looking into is SRE, Site Reliability Engineering. So if you think about building a team, I can strongly advise you to look into these concepts that Google came up with, because one of its goals in SRE is to get rid of heroism. So you want to give developers production feedback. You want to enable your developers to do better in performance as an SRE. And you want to also break down these silos. And it's a huge task. It actually adds up to what we have heard in the previous talk before. And it will not happen from one day to the other. I can, as an advice, only say if you want to look into SRE and do DevOps, this is probably the best way to go, because other companies have achieved it by doing so. But it's a huge journey. Yeah.
Awesome. Thank you.